Now we'll try to apply each of the properties of the special parallelograms with some examples here. For problem number 1, for any rhombus, MNOP. So they already tell you it's a rhombus, MNOP. So I can label it as a rhombus by making all the sides congruent. That's a definition of a rhombus. But decide whether or not MO, so this diagonal right here, is congruent to NP. Whether that's always, sometimes, or it doesn't say never, but then it couldn't possibly be never, but draw a diagram to explain your reasoning. In this case, maybe it appears that each of the diagonals would be congruent, and that could be true. If I made all these right angles, then not only would the rhombus have all sides congruent, but it would be a rectangle as well, which would make it a square. So a square is a rhombus as well. The diagonals would be congruent, MNOP, but the diagonals don't always have to be congruent. I could draw a rhombus like this, where all the sides are congruent. And I think it's a little bit easier to see here by labeling each of the vertices MNONP, that the diagonals don't necessarily have to be congruent in a rhombus. So sometimes the diagonals of a rhombus would be congruent, but not always. And then on number 2, for any rectangle PQRS, determine whether angle PQS is congruent to angle RSQ, whether that's always true, sometimes true, or never true. But here's my rectangle PQR and S. So angle PQS, this angle right here, we want to figure out if it's congruent to angle RSQ, this angle right here. So if you thought about it, this rectangle, it's a parallelogram, so opposite sides are congruent. Opposite sides are also parallel. So in this case, PQ is parallel to SR. It's also true that PS is parallel to QR, but you want to know if these two angles are congruent always or sometimes. They actually always have to be congruent, because if you remember back to our parallel lines and a transversal, so QS could be the transversal for the two parallel lines. These two angles are alternate interior angles, and then the alternate interior angles actually are always congruent. So that would always be true. All right, and then let's look at exercises 3 through 5. It says the diagonals of a rhombus ABCD intersect at point E. You're given the measure of angle BCA, that's labeled in the diagram as 44 degrees. AB is given, it's 9, AE equals 7, and then find each indicated measure. So first, we want to find side length BC. Recall, it's a rhombus, so the definition of a rhombus is all the sides are congruent. DC is 9, AD is 9, and BC is 9. So BC would be 9 units in length. AC, okay. So since it's a rhombus, the diagonals bisect each other. So EC would be 7 units in length, which also means that AC, you're just using the segment addition postulate, would be 14. And then lastly, the measure of angle ADC. So here's angle ADC right there. So to find the measure of angle ADC, we know that this angle, angle ECB, is 44 degrees. It's a rhombus, so the diagonals are perpendicular. All these angles right here are right angles or 90-degree angles. Since it's a rhombus, each diagonal bisects a pair of opposite angles. So diagonal AC bisects angle BCD. That means this angle right here, DCE, is also 44 degrees. So we can use the triangle angle sum theorem to find the measure of the angles in this triangle right here, triangle DEC. You could take 90 and 44 away from 180. So if you take away 90 and 44 away from 180, that gives you 46 degrees for this angle right here. All three of these angles, 90, 46, and 44, have to add to 180 degrees, and then they do. And then diagonal BD bisects angle ADC. So if this part, EDC, that angle is 46 degrees. This angle right here would also have to be 46 degrees. Then the measure of angle ADC for number 5, 46 plus 46 degrees is 92 degrees. All right, and then moving on to problems 6 through 11 on the next part.